Good evening. Welcome back. Let me start with these administrative things. After today, we have only 4 more lectures. Yes, unfortunately. Thank you. I appreciate it. So please be aware on December 18 and 25. Yeah, this year's lectures are given on 23, 24, 25, and maybe even 26. I'm not sure, but I think so.
Expect some Christmas.
Okay, thank you for what you proposed. Thank you for giving Christmas gift to everybody. And then on January, be careful. I want to finish early because usually I don't want to have a lecture when you have exams, but it means we are going to have a lecture on the 8th, which is a very first day of the semester, or maybe -1 day of the semester. Be careful about this. It might be that the door will be closed, so I will open it. So in case, I will repeat it, but in case on the 8th, just come not more than 15. If it is officially a holiday, just come 15 minutes before and I will open the door. Okay. Or maybe the door will be open, but I'm not sure. And the last lecture will be the 15th, and then no more. And it will be recorded, so if ever somebody cannot come, it's recorded. Yes? I think so. No. So I get, except if there is a request to change the time, but otherwise I plan to keep the same time only even for this one. Okay, so let's start. I remind you quickly what we have done last week. It was not too difficult because it was in Rn most of the time. So we know what is a Riemannian manifold. And the good point is Riemannian manifold, you can define an orthonormal basis for each tangent plane because you have an inner product on each tangent plane, so you can really normalize and orthonormalize vectors. And there is one more point for Riemann manifolds, is that there exists when the manifold is oriented. So what does it mean? It means it's orientable and you choose an orientation. When it's orientable, you have 2 orientations and you choose one. So whenever you choose one for orientable manifold, there exists a unique volume form. And what is a volume form? It's a M form. So the M is the dimension of the manifold, such that it gives you 1 when you put the M variables here as the vectors of this orthonormal basis. And I also gave a formula for this when you pull it back to Rm, because this is what we use in computation. So this M form is very useful for defining integrals. This is a key for defining integrals. And for Riemannian manifold, there is one which has a special property. Then for Riemannian manifold, you have also, by definition, you have this tensor field phi, which is symmetric and positive definite, and we can define the length. So we define the length of a curve with such a formula. This is a tangent vector. This is a tangent vector. So this is meaningful. It's a positive number. We take the square root. It's positive because this is a positive definite vector field, and you integrate. So this is a regular integral. And once you have the notion of length, you can define the notion of distance. Because when you take 2 points on the manifold, you can look at all curves from P to Q, define the length of all these curves, and take the infimum, which is bigger or equal to 0, but with the equality if and only if P is equal to Q. So it means with this distance, you can show that this manifold with this distance is a metric space, and I said what is a metric space. Of course, if it is connected, otherwise you have 2 components or more components. And we have also defined what means isometric manifolds, so when the distance is preserved. And there is this Nash embedding theorem which tells you that any Riemannian manifold can be embedded in a bigger space. However, this big space is often too big for your purpose or for what you want to do. So it's also good to look at manifold without an ambient space. Then I quickly went through Frenet frame and Frenet-Serre equation. This is something that we can do in calculus too. It's about one curve in R3. And the last topic was take a manifold embedded in Rn. So we can really use the structure of Rn. We define what means a vector field along M and a vector field tangent to M. So you have your manifold in Rn. A tangent field along M means at every point you associate a vector, but the vector can go in any direction in Rn. While if it is tangent to M, then it means that at every, it's difficult to represent, but at every point, it's tangent to the manifold. So it's a stronger requirement. And any, because we have the scalar product of Rn, any vector attached to a point P of the manifold can be decomposed into one part which is tangent to M, one part which is perpendicular. In fact, if you have this, take a vector which simply starts at one point of M, you can always decompose it into one part which is tangent to M and one part which is perpendicular to M, to the manifold, at every point. And I just introduced this notation with pi prime and pi second prime, which has projections. And then the last construction is take such a vector field, but we assume that it's tangent to M. So at every point, it's tangent to the surface. Then we take a curve, and we define what is called the covariant derivative. So this is, we can take this derivative in an easy way because we are in Rn. So we know what is the derivative of a function in Rn. So it's a function with value as a vector. You take its derivative. It's a vector in Rn, but we take its projection on the manifold. So at the end of the day, this covariant derivative is by construction tangent to the manifold because we take the projection. Okay. So we are exactly here. For any tangent space, for any tangent vector field, we define the covariant derivative, which is again a vector tangent to the manifold. But be careful, it's only defined along the curve. So we have a curve somewhere. First, y was defined everywhere, tangent to the surface. Then the derivative might not be tangent to the surface, but we project it on the surface. So these vectors, which start at every point on this curve, we take the derivative, there are vectors pointing in any direction, and then we project them on the manifold. Okay, so this is this covariant derivative, but please be aware that for this definition, we are using the ambient space, which is Rn, and today I want to get rid of this ambient space. Do you have any question or remark? And yeah, please be aware of these 4 states. All right, so we are here. We start with a vector field which is tangent to M, and we create a new one which is tangent to M. A remark which is quite clear from what is written, I don't really need y to be defined everywhere in order to define the covariant derivative. Look, the only information you need about y is y located at points along the curve or on the curve. So it's a remark. It is not necessary that y is defined everywhere. Its value, it's a vector, but we can speak about value as the value of the function. So its value on the curve, is sufficient. This is just a remark, but it will play a role. So because in this derivative, we only look at y at points on the curve. Then there is an easy lemma about properties of this covariant derivative. So because this covariant derivative is something quite simple. You take a usual derivative in Rn of a vector-valued function and you project. So lemma, we consider y1 and y2. There are two vector fields because we are dealing with vector fields tangent to M and defined on the curve. So it means I don't need to define them everywhere. I just need to have them defined on the curve. And I take also a f, which is smooth function on M. Then what are the properties? D is a linear map in the following sense. D over dt, exactly this covariant derivative is d, the first one, dt, plus dy2 dt. You won't be surprised if you look at the definition. Now, the second one is what happens if you consider df. You have a vector field, so you have rows everywhere on your manifold, and you multiply them by a scalar, so you rescale them. What is the covariant derivative of this vector field rescaled? It's a kind of Leibniz rules. It is the usual derivative df over dt. Okay, no. D of. Okay, I have a small problem. This is what I'm writing is not correct. So probably there is a mistake in the note. I should write D. If f is defined on the manifold, d over dt of it has no meaning. So I need to define it restricted to the curve. So, okay, there is a small problem I realize now. So I need to check this. So I will correct it next week. What I want to say, I don't know if it is a correct notation, but df over dt has no meaning. What I want to do is the derivative of f along the curve. But yeah, as some students have observed, in many books, people are not very precise. And I will mention this later. They just differentiate as if everything is well defined. But most of the time, you need to do some work. I will comment on this later. OK, so I will correct this next week if there is a problem. Plus f dy 1 over t. So I evaluate at t, it's simpler. Evaluated at t, f of t. OK, no. OK, forget this equality. There are many mistakes. Now I realize I haven't been precise enough. Ah, no, but OK. Sorry. Now I understand. This is my mistake. It's not a function on M, it's a function on R. But then is it meaningful? Yes, probably it is meaningful. Yes, because I only look on the curve. So I rescale along the curve. Yes, this is mean. OK, so it's correct. It's f prime at t y times y1 at t. Look, I define. OK, so y1. OK, sorry, I should have been more precise. The function of let's take y1, y2. They are defined. Their function t goes to y of t, which is y of c of t. OK, yes. It's a little bit misleading, the notation. Remember, I mentioned only on the curve it's important. So instead of looking at this function everywhere, I just look at them and I give a new name. Y is a function of t, and it belongs, so y of t belongs to yj, or j is equal to 1, 2. So we can just look at yj. Okay, now it's precise. Yj, it's a function t goes to yj of t, which is a tangent vector at ct. Now it's precise. And okay, I take this function. So I will write a t everywhere at t plus this at t. Now it's well defined. The same here. So f prime plus, times this one plus f of t times dy1 over dt at t. And the third one, yeah, I change the notation because we don't need the functions to be defined everywhere. We should have made it more clear. And the third one, okay, so what is the meaning of this one? This is a scalar product in Rn. So you should look at like this. What is a function? So y1, y2, it's a scalar product, but you need to evaluate it at t, and it's y1 of t, scalar product with y2 of t. And this is a scalar product now in Rn, because this is a vector, this is a vector, you do the scalar product. So what is this? This is just a function. Okay, then if it is, okay, I should have been more careful. If this is a function, it's only the derivative. Okay, I will come back to this statement. I don't want to correct it right now. There are small problems, I realize. Because if this is just a function, I can just take its derivative. Okay. And I just wrote the proof is easy, but it means it's not so easy. I will write the correct version next week. I don't need it for later. And the next part is more important. Okay, sorry. What is the main observation? And this, I already mentioned it last week because there was a question. The main observation is for xp belonging to Tp of M. I consider a curve to M with C at 0 is P and C dot at 0 is this vector. Remember, we had this when we discuss flow. If you give me a vector at a point P, I can always construct one curve which has this vector as tangent vector at the point P. So we consider such a curve. Then the important observation is that dy over dt, so the covariant derivative of y along this curve depends only on this vector and not explicitly on C. This is an important observation. We cannot prove it right now. We will, in fact, look at this in a more general context. It will be visible why this covariant derivative depends only on this tangent vector and not on the precise shape of the curve you choose. And you have an infinite number of curves having this as a tangent vector. But this expression, and be careful, this one belongs, it's a tangent vector in Tp of M. It depends only on this derivative, so on the tangent vector of the curve. So this is an observation that we will see again later. But because of this, we are going to change the notation. And this was the observation made by a student last week. So we would write this dy is covariant derivative. I will write it with a complicated notation for now. For now, this has no meaning. But in fact, it will have a meaning when we are still in Rn. All this is for manifold inside Rn. So the observation is when we define this, it involves a curve. But it turns out that this expression does not depend on the curve. So I'm going to change the notation. And this notation emphasizes more than you can take any curve. What is important is this tangent vector. But with this notation, it means we can even write this nabla of dc over dt y is equal to di over dt. Why I can write this? Simply because here I evaluated at one point. If I don't want to evaluate at a point, this equality is true at any point along the curve, because this is going to be one of them at a certain point, and this is just the covariant derivative without evaluating it at any point. So this is true not only at one point, but at many points. Okay, so I will now state one more result. I hope there is no mistake in this result. And then we are moving to the next section. In a sense, it's simpler because it's slightly more abstract and we don't need the ambient space. So let me state a few results about this proposition. So the framework is M, a smooth submanifold of Rn. We are still in this context. So the first statement, I look at the following function, Tp of M times so what I do, I take one tangent vector, I take a y, so I take one tangent vector and one smooth vector field, and I send it to this new notation, y, which, as we have seen, is an element of the tangent space at P. And the statement is that this map is linear in both arguments. the first. And yeah, again, linearity is something usually not difficult. And in addition, if f is now a smooth function on the manifold, but it's only defined in a neighborhood of P because this is enough, then what is this nabla xp of y? Oh, in a sense, I'm doing the more precise version of what I was doing before. Just this xp of fy. This is f of p times xp y plus xp. Okay, let's just check that it's meaningful. You can multiply a vector field by a smooth function. It is still a vector field. So I can apply this. This is a number times the vector plus what is this? This is also a number times a vector field. Sorry, there is a p missing. A vector field evaluated at p, so it's a vector. So here you have an equality between vectors. So this is the first property that we can check. Yes. Yes.
It has to be differentiable at p.
No. This means your function is smooth in a small neighborhood around p. And you can see the only thing you need, this is well defined precisely for function well just defined at p, and this is the value at p. So it's enough. You don't need to define it everywhere. Now I want to look at something slightly more general. I want to get rid of p, so I want to define it in the essentially the same way as here. I want to do it without evaluation. So if x and y are vector fields on M, then we set I haven't defined this. I define it when I evaluate it at P precisely as this by P. Why? This is a definition. But so what does it mean? It implies that this guy here is a vector field. Because when you evaluate out 1p, this is a vector in Tp of M. So it means this is nothing but a smooth vector field. I should not write imply, but I should write then. So it means we did it for given p here. But I can define this expression, which when we evaluate at p is this one. We know this is a vector in this tangent space. So it means we can check that the smoothness has to be checked, that this expression is a function defined on M, and at every point it's a vector. Okay, so this is the second point. The third point, if this is a bit technical, but it will be nice to have this later, then this xy, we have already seen this kind of things when we discussed precisely the set of all vector field. We have seen that it's a Lie algebra, so this has a meaning, is equal to this guy xy minus this. Okay, so let me finish the statement and then I will make a comment. And the last one, on two scale. We will check that it's meaningful in a second. It's always a kind of Leibniz rule. So let's just check the meaning. Remember, this is a smooth function on M. So we can apply this guy because the smooth function is in particular an element of the infinity of P. And we get a number. And on the right-hand side, we have this, which is a vector. And we do the scalar product with a vector, which is in the same tangent plane. And the same here, we have a vector and a vector, which is in the same tangent plane. We do the scalar product. So this is well-defined, and this equality between numbers. Be careful, here the scalar product is in Rn because we are in this framework where everything is in Rn. No Rn, the manifold might be of dimension m, but is embedded in something in Rn. So I look at the proof. Unfortunately, for now, we don't have the tools to prove it. We will have the tools a bit later when we look at representations. But first we checked already that everything is meaningful. What is important is this, that this is a new vector field, and this property will reappear a bit later, and this one also. But yeah, we don't have the tools yet to prove it. But when you will see in a few minutes, we will be able to do something. And let me just mention an exercise, because I need this equality for xy in vector field. So function on M with value in the set of vectors, on F belonging to C infinity of M. We have or show that something a bit surprising, that look, when we rescale the second entry, so this one, it's a complicated formula. While if you consider this at y, this is f. I'm using the notation of the second one. When we rescale the vector field, it's just linear as a C, linear in this entry, but be careful, it's not linear as R linear, but it means we can factor this function. So this is called C infinity of M linear in, I would say, first argument. The x is the first argument. Look, we can just factor this function out of the expression. This is an exercise which is not too difficult. And the second part of this exercise, which is already written here, so, but I will mention it again. And still in this exercise on gradient x of fy, I just make it the abstract version, f gradient x of y plus x. If you think about it, this is the same, except that on the right, it's evaluated at 1. please remember these two expressions for a second. Okay, so let's try to summarize. We have defined what is a covariant derivative. And I stated a few properties. In the first lemma, it was a bit nasty, but this one is more precise. We have some equalities. But what is important to realize, these equalities can be shown for manifold inside Rn, because we really use a derivative inside Rn. So the next section, which is 5.4, is going to be differentiation on Riemannian manifold, but now without assuming that they are embedded on Riemannian manifolds. So how are we going to proceed? We are going to use the properties that we have seen as definitions. And this is an approach which is often taken. You have some properties in a certain framework, and you abstract them. So it's an abstract version of what we have seen. And in a sense, it's simpler. So it's a definition. So I consider M a Riemannian manifold. And I'm not assuming that it's embedded. I just take a Riemannian manifold. And now I define an affine connection. This is a new word, but you will see that affine connection. And the notation we will see is a bilinear map. It's a bilinear map denoted by this triangle or nabla from a vector field times a vector field. So it means you need two ingredients which are vector field, and it gives you again a vector field written. It's a function of two variables, but we don't write it like this. We are going to write it as we have just seen before, unsatisfying. Two conditions. What are these two conditions? That if you rescale, you have what I mentioned as the C-infinity linearity, C-infinity of M linearity. Now we take it as in the definition for any f. I will write for any f in a second. And the second property is the one written here. In the other variable is equal to, I can just copy y plus f y for any f smooth function on the manifold. You see, we change the point of view. Now the manifold is not embedded, so I don't have this for free, but I take it as a definition. We call a affine connection a map, which is take one vector field, take a second one, it's going to be a new vector field. So take a family of vectors, take a second one, and you get another one. We write it like this, such that it satisfies this relation and this one. And by the way, I can again write this is called C-infinity of M linearity in first argument. And now we understand better why it is the first argument, because if I write it like this, it's indeed the first argument. While it's not C infinity of M linear in the second argument because we have the second term. Oh, there is, yeah, we have the second term. That's it. So I take it as an affine connection. And let me just tell you the end of the story as a motivation. What is it? Why is it useful? You know, what the aim of all this is, if you have somewhere basis which is orthogonal, you want to transport it along the curve and keep it as an orthogonal basis. And this affine connection is precisely going to tell you how you can move such a orthonormal basis along your curve. So it will be useful. However, it's still a long path before we arrive at this, but okay, I gave you the first definition. I take the properties as now part of the definition. So you can wonder, does it exist? Yes, it exists at least for manifold inside Rn. So yeah, we know now it exists because we have Nash embedding theorem. So it means it always exists for all smooth manifold, Riemannian smooth manifold. But this is not the approach. Okay. Question that we can wonder, do we have no, it's no more written, but before I mentioned these two properties, xy is equal to nabla xy minus do we still have this in the general framework? And the other thing that we had before, if I write it in a slightly more formal way, without evaluating, we had this before. This is the second property that we had before. You can wonder, is this still true in the general framework? And you have an additional question. What is this scalar product? Before I put Rn because we were in Rn. Now I'm not in Rn. But do we have something of this type? So this is something we will answer. I need to define one more thing. A map is just a short definition from what we will see first. From xm to xm, I just need this word, is called an endomorphism. We have seen morphism when it's from an object to itself, we call it endomorphism. This word will reappear. And we set end of xm for all endomorphisms. This is not really important, but I will just use this word once. So it's a map from a set to itself. In this context, we call it endomorphism. So we have a definition for this guy. It's a map, a bilinear map, taking two vector fields and sending it to a new vector field, satisfying something or two conditions. Now I give one more definition, which is useful for a Riemannian manifold. With the affine connection. Many also do not write affine, but I think it's better with the affine connection. Blah blah. We set I just give two small definitions. T of xy. I'm just playing with this. So probably you can directly answer the first question. Is it always zero, or do we always have this equality? I wouldn't give this as a definition if this is always zero. So for sure, it's not always zero. Otherwise, I wouldn't define it. And this is called the torsion. We will come back to this. It's called the torsion. And the second thing I define, it's called R of xy. The definition, it's, sorry?
RSION.
Yes, it is. Okay. Maybe badly written, but it's TORSION. And the second one, you should be a bit more surprised with my definition. Minus. This one is called curvature. A torsion of the connection and curvature of the connection. They are not exactly the same. Please, what is this object? So this is for any, we set for any xy vector field. It's just a matter of looking at definitions now. This is, what is this object now? This is again a vector field. This is again an element of this set of smooth vector field. The same here, and we have seen that it's again a vector field. So it means this object is a vector field. What is the second line? Yes, but look, it's precisely what I called an endomorphism. This is why I needed this, not this definition. Because look, you can apply, if you put a z now, for a second, I apply this on a z. Now let's check if I apply this to a z everywhere. It's okay. Just be careful because it's no more an endomorphism when I apply to a z. Let's just check. This applied to a z is a vector field. And so we can apply this one again. It's a new vector field. The same here. And indeed, this take a vector field and send it to a vector field. So it means you apply this to a vector field and you get a new vector field. So it's precisely the definition of an endomorphism. It's a map which take a vector field and send it to a new vector field. I can erase the z. But yeah, you should just observe that if you apply a z on this, you get a new vector field. Yes?
Just want to check. So like the curvature they just defined there, is it like in GR framework, general relativity framework?
I haven't spoken about general relativity yet. Everything is related, of course. Okay, I just give two definitions. Now observation. And this is probably a nice exercise, not difficult, just to check that you understand what is going on. With the definition, you don't need to do more than just understanding the definition. If you define this, and if I define this goes to, no, sorry, the first one is a t. And the second one is t. This is r of So please, we observe that this is a vector field. And this is again a vector field because I apply it to a Z. The claim is these two expressions are C infinity of M linear in all arguments. So what does it mean? No, it's no more here. What does it mean? It means if you put a F here, you can put it here. It's linear in as linear in terms of function. Or if you put it here, it's also linear in this argument. And the same if you put a F here or F here or F here, you can make it here. So as I said, it's not difficult, but you need to go through the definition and check. So it's C infinity linear. So it's not only linear like a vector space, but you can even put coefficients which are smooth functions, and it's still linear for them. Okay. You just need, we have seen only one definition, so this is the only thing you need. So this is even for first year. You haven't submitted any exercise the first year, so you can look at this, it's not difficult. Now, we say that this guy, this nabla is torsion-free. Torsion-free. This is just a kind of definition. We say that it's torsion-free or symmetric if, of course, T of xy is 0 for any x and y. This is quite natural. Torsion-free or symmetric if this is like this. In addition, so if in addition we have a second property, if now x of y1, y2 for the third time I write this. If we have such an equality, but now we need to understand it. We are no more in Rn. So what means this? It's not, if, remember, y1, y2, if I evaluate at a p, a definition, it is pi p of y1 p, y2 p. What is the meaning? We have the Riemannian metric, which define the scalar product. So this is a vector on one tangent plane at P. This is again a vector in the tangent plane at P. We have this function which define an inner product. So this is just a number. So it means this, when I evaluate at a point, I get just a number. So it means that this notation y1, y2 is a smooth function on M. And I gave the definition just above. So now let's check that this is meaningful. Vector field apply on a function, it's a number. That's, no, sorry. A vector field apply on a function is a new smooth function. It's when we evaluate that it gives us a number. It's a new function. And here we have indeed the same expression that's here. This is a vector field times scalar product of vector field. So it's a function and this is a function. So everything, both sides of these equalities are in fact smooth function. All of them belong to smooth function on M. Think about it. So if the connection is symmetric or torsion-free, and if this equality holds, we say that the connection is a Riemannian connection. It's a definition. Or there is another name, or Levi-Civita connection. Yes, heavy do. Sorry? We are dealing with Riemannian manifold. What is a Riemannian manifold? Remember, a Riemannian manifold is a manifold with what I call a Riemannian metric, which is a symmetric tensor, bilinear tensor field, and which is definite positive definite. So I started with a connection and I mentioned two properties. If it is torsion-free, which means this, and in addition, if we have this equality, we call it a Riemannian connection or a Levi-Civita connection. Why is this equation is important here? Because look, it makes a link between the connection and the metric. In this equality, we have both, and it's visible here. On the right-hand side, you have the connection and the metric, while on the left-hand side, you don't have the connection. So this equality makes, or is you can think about it as a compatibility between the connection and the metric. It's a condition which involves both. Oh, remember when we were in the previous chapter, these two conditions were satisfied. This torsion-free was satisfied. You can check the meaning. It was one property of the theorem I mentioned, and I also mentioned this one. So remark, the connection. I didn't speak about connection at that time, but if you check the notation, it was already a connection. The connection introduced for submanifolds of Rn in the previous section was a Riemannian connection because these two conditions were satisfied. This is a first observation. Oh, in fact, there is only one observation because I already mentioned this. I already wrote that this is compatibility condition. I already mentioned that if you look at this equation, it's really a compatibility between here you have no connection on the left-hand side, while on the right-hand side you have the connection. Okay, so it means we have defined what is a Riemannian connection. We know that for submanifolds of Rn, what we have defined before is Riemannian. Question, what about the abstract framework without the ambient space? Theorem for any Riemannian manifold, any Riemannian manifold, there exists a unique Riemannian connection on M or any. Okay, so it makes the story consistent. As a submanifold of Rn, we define a connection and it has the properties I just mentioned here. Now you can wonder in the abstract setting, if you are not embedded in Rn, does it exist, a Riemannian connection, and is it unique or not? And the answer is yes. For any Riemannian manifold, there exists only one Riemannian connection. So only one connection which has this property. And there is a nice exercise. I don't want to state it completely, but there is an expression which is called Koszul formula. Here's the Koszul formula, which gives you an expression for this guy. So you can define, or you can check an equality. You can give an expression for this Riemannian connection with a long right-hand side. So it's a way, here it's existence and uniqueness. If you look at this exercise, with this exercise, in fact, you prove existence. You prove existence. Why? Because I gave you a certain formula, and you can check that this formula satisfies the property I mentioned. So you check that this connection satisfies what is required. So, but it's not a uniqueness proof, but at least it proves the existence. Okay. So if you think about it, this new section is a bit simpler because I took a definition of affine connection. I took it as a definition with two properties, and then I gave a definition of torsional curvature. I mentioned what is a Riemannian connection, so it has to satisfy two properties, and it turns out that on Riemannian manifold there is only one. But now we want to have something concrete. We want to do some computation. So in order to do computation, you need chart, because you can do computation only when you are back to Rn. So it means you have an abstract manifold. You need chart, so it means you need to send locally on Rm. And this is U, I usually call U and phi. So you need to represent locally your manifold as a subset of Rm. Be careful, this M is not the Rn I mentioned before. I'm not saying that this manifold is embedded, but by definition, a manifold locally, it looks like Rm. So let's look at concrete formula. With, it's with a chart. And I usually use U phi for chart. And when we have a chart, we have and the coordinate frame. I hope you remember what is the coordinate frame, which I denoted by E1P up to EMP. This is a basis of the tangent space. So this is a basis of TP of M for, of course, for P inside U. So when you have a chart automatic, so a chart is locally this part, let's say this circle looks like the blackboard, and a coordinate frame is at every point on this, we have tangent planes, and this guy gives us, this is a basis of these tangent planes. So on each of them, we have a basis. Okay. So the first lemma, still observe that before the lemma, something I haven't mentioned, but it's quite clear. If I look at the map, P goes to E, J, P. P is inside U. Look, this is a tangent vector. But it means that if I look at just EJ and I put a dot, or I simply will not put a dot, I will just call it EJ. What is this object? It takes any P and send it to a vector. So it means this is a vector field. It's a vector field defined on U. Or I can also say it's belong to this. So I haven't mentioned this, but you can look at these, the component of this basis as a vector field. And I will use it in a second. Is it clear for everybody? At every P, you have a tangent vector. So if you just look at the function mapping a point on the manifold to a vector in this tangent vector, this is precisely the definition of a vector field. Okay. Lemma. So I will use these things. Let M be a Riemannian manifold of dimension M. For me, it's always the same. By the way, at Tutai, you change my convention. You call it capital M, a manifold of dimension N. It is not so good. M, a manifold of dimension M. Gamma, any affine connection. So I don't need, it's a bit more general, any affine connection, in the sense that I'm not asking that this is a Riemannian one. I just take any and you phi a chart. Then there exists m power 3 functions. These functions are called gamma, and they depend on 3 parameters. They are defined from U to R. There are m square such function because I, J, and K are both in 1 up to M, which define gamma uniquely. So I, J, K are between 1 and M. That's why we have m power 3 function. And they are called, some of you probably know it, they are called Christoffel symbols. So it means any connection is fully defined by m⁻³ search functions from U to R. Define uniquely, I should just say on U. Everything is localized on U. And in fact, I will do the proof or part of the proof because we learned something from this proof. Yes.
Chart we chose, is it an arbitrary chart or must it be one of the chart in a maximum atlas?
It is. We are dealing with smooth manifolds. So you have to take the charts which are in the atlas. Yes, because otherwise there is, if you take an arbitrary one, there is no compatibility with the smoothness. So you have to take a chart in the atlas. Yes, it's by default. So what is a proof? I think it's interesting. I'm going to set I just mentioned before that these Ej and Ek are vector fields. So precisely, I can define nabla applied to a vector field, or nabla of first vector field, second vector field. Now, this is again a vector field. So I can decompose it on the basis. So it means I always have this equal to a sum I1 up to m of gamma JKI EI. And I will write it again or equivalently. We will see why we have this. This EJ, comma P EK is equal to sum I1 up to M gamma JK at P E I at P. Look, this is a vector in the tangent space Tp of M. We apply it to vector field. We know that everything has to be inside Tp of M, but we have a basis, and I call the coefficient of this basis with gamma. Here we have a J and a K, so I put a J and a K, and I sum over I. This is always possible. This gives me a definition of what is gamma JKI, because it's a basis, so every vector can be decomposed in this way. This is for any P belonging to U, and this is simply without evaluating. This is the same equality, but I don't put a P here, but it's the same. Now, for X, which is going to be, I decompose, I use this basis a lot. EJ and Y equal to sum AK EK. These are two vector fields we define on U. Let's say I define everything on U. And again, I can decompose as I did before. Then we have, I want to show that the connection is uniquely defined by these family of m⁻³ symbols. So I'm going to compute this guy on a Y. Okay. Now I'll use the linear, I'm going to use all properties we have seen. This is a sum Bj Ej, sum J, sum K, AK, EK. Okay. What we have seen that this is a sum on, it's linear, so it's a sum of EJ. I go slowly, EJ of apply to the sum AK, EK. I just use that it's linear. We have seen this property. This is a smooth function. Oh, maybe I should have written AK and BJ are simply smooth function on U. They are coefficients of this decomposition. So this is a property which is from the definition. And then it makes, it's also linear, so I can put the two sums here. K, this is sum over K. BJ, EK, EK. Okay. Now you have to be careful. You're not allowed to put this here because it's not linear in this argument, but we have a property. So this is equal to sum AK BJ of, we have B. I'm just using the property which were in the definition. I'm not using anything more than this. So what was not allowed is this. I cannot do it, but this is a correct thing. And now look, this guy is what I define here. And if you just think, here you can sum these two guys, it makes precisely X. So at the end of the day, I will write it in the next here. What you obtain, if you put this together, you obtain that this is equal to this. I let you do the missing step. It's only one step. EAI plus some AK of AK. No, yeah, AKB. Okay, this is what we obtain. So what does it mean? Look, we started with the connection on, I can also write it as connection on any pair XY, because this is the initial notation, is equal to something which has no more any connection. It's simply in terms of the Christoffel symbol. Of course, X and A and B are part of the A, X and Y, so I cannot eliminate them, of course. But look, the only ingredient are these Christoffel symbols. So I already have shown what I wanted. This connection is explicitly expressed in terms, and uniquely expressed in terms of the Christoffel symbols. And so gamma, oh yeah, nabla, uniquely, it implies that uniquely expressed in terms of is gamma JKI. And you have more, but I don't do it. And also, this expression satisfies the properties of an affine connection. So what do I mean by this? If now you only take this as a definition of this, you can check that the properties that the affine connection has to satisfy are satisfied by this. So this is a way you show that this connection is defined by these symbols, but when you have this expression, when you define a connection with this expression, you have an affine connection. Okay. So this is, it's not the full proof, but it's a good sketch of the proof. And now observation. Or do you have any question? I told you, in a sense, the abstract version is simpler because we have some precise rules and we know what we do. While in the previous section, I did a mistake because it was not so precise, but I will correct it. No, not yet. There is no reason because not all connections are torsion-free. And the statement was for an arbitrary connection. It was not for the Riemannian connection. In particular, but it's good to mention this, in particular, what we get, T of xy, heavy dose, this is now your exercise since you mentioned it. I recall the definition. Is equal to, it's almost trivial. So maybe it's too easy for you. I use the same notation as before. I mean, I keep the same notation. In particular, with same notation. So it means the x and the y are the one I have introduced before. You get this conclusion heavy do. What do you conclude from this about torsion-free? Yes, but what is a necessary and sufficient condition for being torsion-free?
But the second term cancel, so it's 0, but not.
Yes. So from this you obtain that gamma is torsion-free. So this guy, this expression is 0. If and only if gamma ki is equal to gamma kji for any I, j, and k. This is the answer to your question. So by the previous statement, any connection is linked to a family of Christoffel symbol. This connection is torsion-free if and only if these symbols are, this is called symmetric. The symmetric properties, symmetric in these two indices, k and j. So now you know not all connections are torsion-free, but if the Christoffel symbol are symmetric in j and k, yes, your connection is torsion-free. So it means for the one in the Euclidean setting, it was torsion-free because the Christoffel symbols were symmetric. So now I recall something. I just recall something I introduced 1 or 2 weeks ago when we started with Riemann connection, with Riemann metrics. No. So for Riemannian manifold, you have the metric. You can evaluate it at a point P. It's a bilinear map on the tangent space. So you put 2 vectors on the coordinate frame and it gives you a certain number. And we have seen the matrix is denoted by Gij of P. I corrected the mistake you mentioned a few weeks ago about the determinant. So this is now a matrix. And the inverse, its inverse is denoted by, so be careful. You have to be a bit precise about where you put the indices, because when you put the indices on the top, it means the inverse of the matrix. This matrix is invertible because it's positive definite. So we have introduced this. This is a notation for the matrix. It's a M by M matrix. And I'm using with the upper indices when it is the inverse. Why I introduced this? Because remember, for the Riemannian connection, there is this compatibility condition I mentioned. There was an equality, and I said on one side you can see the connection, in the other one you don't see it. And this is a compatibility relation between the metric and the connection. So now I want to express it in terms of this Gij. So it's a lemma, and it is probably the last one I'm going to write for today. Lemma for M Riemannian manifold. And for this connection, the Riemannian manifold, so the only one having the two properties mentioned, it's torsion-free and satisfies the compatibility condition. The Christopher symbol, the Christopher symbols are given by and what I'm going to write shouldn't surprise you too much. Is gamma jki, it's 1/2 the sum over sum over L of oh, good. So you will complain. Please try to complain about this expression. Only in particular, you should complain. Or maybe you, Theo, you should complain. Where DGH. Okay. First, do we understand this expression? We can check this is, the good point is it's symmetric in K and J, and it has to be like this because the Riemannian connection is torsion-free, so it's symmetric. So these two terms can be exchanged, and here we have the two terms where this is again symmetric. So it's symmetric. This is a good point. We have the inverse of the matrix. If you want, you can evaluate everything at P. Like here, it's not evaluated at P. So if you can evaluate this as P, evaluate at P, evaluate everything at P. But is this well defined? Ole, you're expert. Is this well defined? No, this is not well defined because G is a function living on the manifold. And I'm taking a derivative with respect to xk. What is the meaning? So this is not meaningful. This is what you find everywhere. And you are facing this problem. And you are also facing this problem. In fact, when you read this, what people are hiding is that this is equal to d of the composition dLj composed with phi minus 1 because we have the manifold and we have U on the manifold, which is sent on Rm. This is phi. So phi minus 1, take something in Rm, send it to U, and then this is meaningful because this function takes point in U and give you a number. Yes, I know. So I can now this composition is really a function defined here. So I can take a partial derivative. I need to evaluate at P, but I cannot evaluate at P. It's meaningless. So what is the correct expression is phi of P. Where is P? P is indeed here. So you first consider its image. This is phi of P. So you go from here to here, and then G gives you it's a function on this with value in R, so you can differentiate, and then you evaluate at this point. So when people write something like this, and you face the same problem in your report, when people write something like this with a function which a priori is defined on the manifold derivative with respect to something in Rn, what they have in mind, you can take it as a definition, is this, because this is the only expression which is meaningful. So be careful, in many books, you have such things which are not written. Because of course, when you write things properly, it's longer. That's reality. But at least everything is well defined on this side. Okay, so I finish here. Why I said you shouldn't be surprised in the following sense. There is this compatibility between the metric and the connection. The connection is completely defined by these symbols. Then these G are completely defined by the metric. So both, they define each other. No. The metric defines the Christoffel symbol. I'm not saying that the Christoffel symbol defines the metric. I don't think so. Okay. And yeah, I stop here, but the proof of this is not so difficult. I put a link, or I gave a reference where you can find it. You just use all the expressions and with a chart. Okay.